All right, welcome to The Explainer. Today, we're diving into a concept that sounds like it's from the future, but it's happening right now. We're talking about a way to solve one of the biggest problems in tech by powering a computer with, and I'm not kidding, empty space.
So let's just start with that question right there. Could a computer actually run on empty space? It sounds completely wild, right? Straight out of science fiction. But you're about to see, this idea is actually grounded in some very real and frankly, very strange quantum physics.
But before we get to the crazy solution, we really need to understand the problem, and it's a big one. Quantum computing is without a doubt a revolutionary technology, but it has this massive hidden energy cost that we have to deal with. Just look at this number for a second. 260 megawatts. That's the projected power draw for a 1,000,000-qubit quantum computer. And 1,000,000 qubits, well, that's kind of the magic number for solving really world-changing problems. To put it in perspective, 260 megawatts is about what a small nuclear power plant puts out. So you can see, this is the real crisis. The path we're on right now, it's just not sustainable. And the craziest part? Most of that energy isn't even for the actual computing. Nope, it's for the giant cryogenic refrigerators needed to keep the quantum bits, the qubits, stable at temperatures literally colder than outer space. It's an energy nightmare. Okay, so with that huge problem in mind, let's dive into the solution, which honestly seems impossible at first. We're talking about harvesting usable energy from what we all think of as the void, from empty space itself. So how is this even possible? Well, it all comes down to a really weird phenomenon called the Casimir effect. See, it turns out that the vacuum of space isn't really empty at all. It's actually fizzing with these virtual particles that just pop in and out of existence, creating a kind of constant background quantum energy. This is a perfect way to picture it. Imagine those quantum fluctuations are like waves in an ocean. Now, if you put two ships really close together, the big, long waves can't fit in the tiny gap between them. But all the waves on the outside are still there, pushing inward. That outside pressure forces the two ships together. And that push, that's a real, physical, measurable force. And, this isn't just a thought experiment. Researchers are actively working on how to harness this quantum push for actual power generation. But here's the catch. The force itself is incredibly, incredibly tiny. To make it useful, you've got to find a way to really crank it up. So, how in the world do you amplify a force from the vacuum? Well, the secret lies in creating a very special material. We're talking about engineering something at the atomic level specifically designed to grab and magnify that tiny quantum force. And the material they're using is graphene. Now, this is where the real magic happens. It's a process called co-doping. You take a sheet of graphene, which is just a one-atom thick layer of carbon, and you pepper it with both lithium and nitrogen atoms. The lithium atoms are really generous. They love to donate electrons. And the nitrogen atoms create these little pockets that are eager to accept them. This creates this incredible push and pull of electrons all across the material. And that electrical tension makes the graphene way more interactive with those vacuum energy fluctuations. And here's the key part. It's not just an additive effect. It's what's called a nonlinear synergistic enhancement. It means that 1 + 1 doesn't equal 2 here. It equals something much, much bigger. And here's the proof in the numbers. And the results are just wow. At a tiny separation of 100 nanometers, the force on plain old graphene is about 1.2 nanonewtons. But look what happens with the co-doped material. It jumps all the way up to 9.9. That's more than an 8-fold increase, an 8.2 times multiplication of the force you can actually harvest. It's incredible. By engineering the material atom by atom, you can basically turn up the volume on the energy of empty space. Okay, so we have the effect. We have the supercharged material. Now, let's see how you put it all together to build an actual engine. An engine that could power a quantum computer. Now get this. This special graphene has an amazing side effect. It doesn't just harvest energy, it actually makes the quantum computer better. It boosts a super important metric called quantum coherence time by over 200 times. In plain English, that means the fragile qubits can hold on to their quantum information for much, much longer, which makes the computer way more powerful and less prone to errors. And of course, scientists don't just guess at these things, they verify it. They use these complex simulation tools to measure these performance gains with incredible precision. A variable like you see here, T2 times, is literally tracking how long each qubit can stay coherent and stable, right down to the microsecond. So what's the end result? It's a quantum Casimir engine. The Casimir force makes these tiny membranes of the special graphene vibrate back and forth, kind of like microscopic drum heads. That mechanical motion gets converted directly into electricity, and it generates a really substantial 170 watts of power for every square meter of material, all pulled directly from the quantum vacuum. The implications here, they're just hard to overstate. This completely flips the entire script on the energy footprint of high-performance computing. It's a total game changer. I mean, just look at this. A standard quantum computer costs almost 400 grand a year in energy for every 1,000 qubits. This new system, it doesn't cost anything. In fact, it can make you money, about $18,000 a year, by selling its extra power back to the grid. So the final payoff here is just incredible. You've got a quantum processor that powers itself. You're looking at a 99% cut in operating costs. But the biggest deal? This is computation that is carbon negative. It's not just self-sufficient, it's a net producer of clean energy. It is, quite possibly, the most energy-efficient form of computation ever demonstrated. This kind of breakthrough just throws the door wide open to a whole new era of sustainable technology. And it leaves us with one last really exciting question to think about. If we can pull usable energy out of thin air to power the most complex machines we've ever built, what else can we power?